So today we're going to talk about the yield of a chemical reaction. Now, if you've been brushing up for your G1 or G2 test for driving, yield signs are the big yellow triangle ones, and they mean let a car in front of you, but if there's no car, don't stop. Yield of a chemical reaction means how much product we get, and usually it means how much of the product that we really want do we get. And we can look at it in two ways. There's the theoretical yield. A theoretical yield is the amount of product that we predict we will get, calculated from the equation, and the measured amounts of the limiting reactant. So the limiting reactant is something that we've covered in another video, and we use the mass-to-mass problems. So what we mean by limiting is that something runs out first. Okay? So whatever we run out first, that's what we use to calculate our theoretical yield. This is all nice and dandy. We do this with calculators and periodic tables, and that's nice. Unfortunately, real life is different. Our actual yield is the actual amount produced if we do this in a laboratory. And unfortunately, our actual yield is usually a whole lot lower than our theoretical yield. If we get 50% of what we thought we should, that's a pretty good yield in industry. In fact, on average, some will give 100% yield. Some reactions behave well and always give everything that they're supposed to. Sometimes we get 30% or even less, and sometimes industry is okay with that. Why? Why might the theoretical yield be different from the actual yield? Sometimes the reactants are not pure. That means what we thought was sodium chloride might have had a few fluoride ions in it, maybe a few bromine atoms in it. Maybe the sodium chloride got mixed with sand, and so it's got silicon dioxide. If the reactants aren't pure, then that means in our mass-to-mass calculation, we had some reactant that's not actually reactant. Sometimes the reactions do not go to completion. That means that even though we think we do our excess and limiting reagent stuff where our limiting reagents should be all used up, sometimes it's not. A side reaction might occur. We think that all our sodium chloride is turning into something, but sometimes the sodium chloride is turning into something else. Sometimes we lose our product. We did actually make it, but when we filter it using filter paper or use other means to isolate it, or when we transfer it from one container to another, we spill a little bit. And sometimes our product may be contaminated. This is what happens when our actual yield is higher than our theoretical yield. We think our product is pure, but it's got water in it, or it's got another product, or we've got unreacted reactant in it, and we get extra stuff. The calculation is usually pretty straightforward. If we want a percent, we want to know how much of what we expected is actually there. So it's the same way you calculate your mark on a test. If this was a test, it would be the theoretical yield, so all the marks possible on the test, maybe the test was out of 50, and the actual yield, how many marks you actually got. Actual divided by theoretical times 100 gives you the percent. Let's give it a try. What's the percent yield of 60 grams of calcium carbonate is heated to give 50 grams of calcium oxide? All right. In this case, what is the percent yield? Is 60 grams of calcium carbonate is heated to give 15 grams of calcium oxide. So here, this value is our actual. This is how much a reaction actually occurred. In theory, calcium carbonate should decompose under heat into two things, calcium oxide and carbon dioxide. First thing to do is to write a balanced chemical equation for our theoretical yield. Theoretical yield is the exact same calculation as a mass-to-mass calculation. We started off with 60 grams of calcium carbonate, and we want to know how many grams of calcium oxide we should get. Is this balanced? Calcium and calcium, 3 oxygens and 3 oxygens, 1 carbon, it's balanced. So we can do 60.0 grams of calcium carbonate, and we need to find the molar mass, grams of calcium carbonate. 40.08 for calcium, carbon is 12.01. And 3 times 16, 100.09. Sorry, yep, 09. grams per 1 mole of CaO3. The mole ratio happens to be 1:1, 1 mole of calcium carbonate to 1 mole of calcium oxide. And one more calculation. Sorry, 1 mole of CaO has a mass of 40 where did it go? Calcium is 40.08 plus oxygen 16.00, 56.08 grams. So times 60 divided by 100.9. We get about 33.617 grams of CaO, and this is our theoretical. All right. To get our percent, we take our actual divided by our theoretical and times 100. So I know I shouldn't put two equal signs like that, but I'm running out of fit space. And we end up with about 44.6%. Not bad for a reaction. I knew this was my actual yield because it told me the mass of product. It gave me the mass of one of the reactants. I used the balanced chemical equation. I did a mass, and the mass became moles of that substance. I used the balanced chemical coefficients to get the moles of the substance I was interested in, same one here, and then I used the molar mass to get grams. I divided and times by 100 to get the percent.